Hey everyone, welcome back. So in the last video, we talked about t-test. So when do we apply the t-test? When our sample size is small and or the population variance or population standard deviation is unknown. So here's how we calculate the test statistic. X bar minus mu over sample standard deviation divided by the square root of n. And t follows the t distribution with n minus 1 degrees of freedom. And also we discussed about 3 types of t-tests. So first one is one sample t-test, which is used to verify a claimed population mean, while the two sample t-test is used to compare two population means. So the last one pair t-test compares the means of the same group and with different conditions such as before and after the treatment. And we had a question at the end of the video. So what if we want to compare the means of more than 2 groups? So you may want to do multiple t-tests for each paired groups. However, it is not recommended to do so because there are several issues with the multiple t-tests. The first one is you have to do k choose 2, which is k times k minus 1 divided by 2 pairwise t-test. And the second one is the probability of making at least one type 1 error is 1 minus and 1 minus alpha to the power of k, where k is the number of t-tests. Alpha is the significance level. So here is how we calculate the probability of at least one type 1 error. So for one single t-test, we have the probability of alpha to make a type 1 error. And then the complement is not making a type 1 error is 1 minus alpha. And then for k tests, then the probability of not making any type 1 error is 1 minus alpha to the power of k. And the complement again is the probability of at least one type 1 error is equal to 1 minus alpha to the power of k. Okay. So as you can see that the more t-tests you perform, the greater the cumulative probability of making at least one type 1 error. So if you have 100 t-tests, almost certainly that you will make at least one type 1 error. Okay. What are the ways to fix these issues? So the first one is Bonferroni correction, which sets our new significance level to alpha divided by k. Okay, k is the number of tests. But this can be overly conservative, so probably you will not be able to detect any difference or get any significant result. The second one is analysis of variance, which is the topic of this video. Let's dive into it. So variance measures the dispersion of a set of data points around their mean, right? And there are 2 kinds of variance in ANOVA. The first one is variance within groups, which is the dispersion within each group. And the second one is variance between groups, which is the dispersion between the group means. And essentially, ANOVA compares the variation within groups against the variation between groups. Let's understand the ANOVA from intuition. So in which scenario are the means of 2 groups significantly different? In the first scenario, we have 2 normal distributions with means of 8 and 11 and a standard deviation of 0.5. They barely overlap, right? And the second scenario, the 2 groups have means of 8 and 9 and the standard deviation is unchanged from the first scenario, okay? And the curves starting overlap, it may suggest that a smaller difference in mean. And the last one has the same means as the first scenario, but with a larger standard deviation of 2, so resulting in much more overlap, and which may indicate that the difference in means may not be as distinguishable due to the increased variance with each group. So there are 2 variabilities. First one is between group, second one is within group. As we compare the scenario 1 and scenario 2, we can see that the smaller the distance between the sample means, the less likely the population means will differ significantly. For the within group variability, as we compare scenario 1 and scenario 3, then we can see that the greater the distance between sample means, the less likely population means will differ significantly. And then here is how we calculate the variance between groups. It's also called sum of squares between. So SS between is equal to the sum of ni times x bar I minus x bar square. Okay, so k is the number of groups, and ni is the number of observations in the group I. And x bar I is the mean of the group I. And x bar is the overall mean. And the variance within groups, also called sum of squares within. So sum of sum, the square of xij minus x bar I. So here the xij is the j's observation in the group I. And then we have the F-statistic. So F-statistic is equal to sum of square between divided by k minus 1 over SS within divided by m minus k. So SS divided by degrees of freedom is also called the mean square. So the test statistic follows a F distribution with two parameters, which are degrees of freedom. Here is what a F distribution look like. The F distribution is skewed to the right, and with the degrees of skewness decreasing as the degrees of the freedom increase. Okay, so as you can see, the peak actually move to the right side as the degrees of freedom increase. So here are the assumptions of ANOVA. The first one, it is independent and random samples. The second one is the population distribution is approximately normal. And the last one is equal population variances. So the rule of thumb is the largest variance over the smallest variance should be less than 2. Now we are going to look at one example. So you are testing the effect of 3 different call to action button designs on your e-commerce website. The metric of interest is the click-through rate, which is the percentage of visitors who click the button. You randomly assign visitors to one of the 3 designs, A, B, or C, and record their CTRs. Okay, the design A has the average of 6.2% click-through rate, and design B has 7% CTR, and design C has 6.5% of CTR. And then the null hypothesis is mu1 is equal to mu2 and equal to mu3, and the alternative hypothesis is at least one mu I is different. Now we prepare our data. So we randomly generate some data based on the mean and standard deviation. And then we convert it to a long format, which has 2 columns. One is design and the other is percentage. We plug in the data, df, to the ANOVA function, then we summarize the result. So this is the degrees of freedom on the numerator, which is k minus 1, and this is m minus k. So here is the sum of squares, and for the numerator SS between, and this is SS within, and then this is MS between, and this is MS within, and this is the F value, which is 32.62. And here is our p-value. Okay, as you can see that p-value is less than 0.05. So we reject H naught at 0.05 significance level. And we conclude that at least one of the designs has a different CTR. So Tukey's HSD test can be used to determine which groups are different from each other. And the test statistic is Q is equal to the sample mean difference between 2 groups divided by the square root of ms within divided by n. And the critical value is q alpha k and n minus k, which can be calculated in R. And then if the test statistic is greater than the critical value, then we reject the HO for the pair of groups. So we can just plug in the ANOVA result to the Tukey SHD function. And then here is the Tukey SHD test result. So for design A and B, here is the estimate difference. and then here's 95% confidence interval, and here's the p-value. So as we can see that we got 2 significant results and 1 insignificant result. So we actually reject HO for the pair of groups A and B and B and C. And we fail to reject HO for the pair of groups A and C. And that's it for ANOVA. If you find this video helpful, please like and subscribe. Thank you for watching.